Okay. So,
So I had a
yeah, go
question
for
with
it.
this one because the first three answer choices, I know it's between the first three answer choices, but I can't like tell why it's the third one and not the other two.
Okay. So, first, I guess I'll ask you, why is it between those?
Because the hydrogen,
Okay. So,
because it's an aldehyde group.
yeah, exactly. And so, what are these two?
They're carbonyls.
They're carbonyls, but what specifically? Yes,
Ketone?
they are ketones. And so ketones would be in what region?
They are.
Is it 3 to 5? Or does no one answer it?
They're in the alkyl region. So that's like 1 to 2.5. So these
And we
ones,
know that for West exam, right?
sorry,
We have to
repeat
know
that.
that regions
Yes,
memorized.
you have to have them regions memorized.
Okay.
All right, so between these three, you were totally right. The thing you have to look at is it's a singlet, right?
Mm-hmm.
So let's draw in all these hydrogens. And we know we're looking at this one because you told me we're looking at the aldehyde hydrogen because it's 9 to 10. And then let's see if this has any neighbors, right? So 1, 2, 3. This one does have one neighbor, so it's a doublet. Here, 1, 2, 3, it doesn't reach anything, so that is a singlet. Here, 1, 2, 3, it reaches 2 hydrogens, so this one is a triplet. Does that make sense what I just did?
Is it the neighboring hydrogens?
Yes, so for the neighbors, it's within 3 bonds, right? So I just went 1, 2, 3. Oh, I don't know why that corrected to like a thing. But since this has a neighbor, it's going to be a doublet because we do n plus 1.
Okay, okay. Yeah,
Yeah,
I got that.
cool. So then this is specifically saying it has to be a singlet. So out of these answer choices, the only one that doesn't have any neighbors is number 2. So the answer would be this.
And they were in the carbonyl group, and that's because it was the H to a double bonded O to an R group.
Yes. So around 9 to 10 is going to be, you can think of it just as an aldehyde. So as you said, R with a hydrogen.
Cool.
Yeah.
Got it. Got it.
Cool. So does this answer your question? Any other questions about this one?
Go complex splitting as well.
Yes, we can definitely do complex splitting. So let me just jump into this one. And all right, we can ignore that part. That's fine. So complex splitting, let's say we have some molecule like this, right? And I'm telling you to find the multiplicity of this hydrogen. We'll call it hydrogen B. We can call these ones hydrogen A. And this one's going to be hydrogen C. So this is different than normal splitting because here we have sp2, here we have sp2, and here we have sp3. So if we're looking at hydrogen B, we can see that one of its neighbors is sp3 and the other neighbor is sp2.
Mm-hmm.
So this essentially translates to different J values. And the way this would be like written on a test is JAB, which is this J value.
Can you explain J value again? I'm sorry.
Yes, no worries. So J value is, it's really, really complicated what a J value is. So for the purposes of this class, all you have to know is when you have one signal, all of its neighbors are going to cut it into two peaks, right? So this kind of goes back to the tree diagram. Don't worry about the tree diagram. I'm just showing you like conceptually what it means. So every time we split it into two peaks, there's a distance right here, and that distance is the J value. So it's essentially just the distance between the two peaks when a neighbor hydrogen splits a signal.
Is it two different peaks or like the same? It could be the same, or it doesn't matter.
So it's going to be one signal, and it's going to be two separate peaks. Gotcha. So like when we say a doublet, what we mean is it'll look like this on a spectrum, right? And that's because it was split into two peaks. So hello, Dustin. I saw that you just joined. All right. So
this.
Yeah, go ahead.
No, finish.
Okay, so I was just going to say that JAB does not equal JBC. That's what he'll tell you because this J value is going to be different than this one. It doesn't matter like what they actually are, like what the actual values are. You just have to know that different hybridization equals different J value. All right, so did you have a question?
I was just going to ask, well, you're going through this problem, but I think I have the answers, so I just want to see if I was correct or not. But I'll wait.
Okay, sounds good. So when we have complex splitting, we're going to use a different equation. We're not going to use n plus 1. We're actually going to do n1 plus 1 times n2 plus 1. And n1 and n2 is just neighbors. So we're going to say the left and the right neighbors. And just to make things more straightforward, I like to use the smaller number first and the larger number second, but you could do it either way. It doesn't really matter. So n1, we're going to say is HC because there's only one neighbor. So I'm going to say one neighbor plus 1. And we're going to multiply that by the other side where we have 3 red neighbors. So I'll say 3 plus 1. So at this point, it's just simple math. Oh, apparently not that simple. We're going to say 2 times 4, which is 8. Ta-da! So we can say that the multiplicity of this is 8, but it's not going to be an octet. Instead, it has a special name. And the way we get that name is we're just going to name either side. So we'll start with this side, doublet. The multiplication sign just turns into an of. And then name the other side. So this guy is a doublet of quartets, and the multiplicity is 8. And just in case this helps you kind of visualize it, it'll look something like this.
So this is for the blue one, right?
Yes. Bam. And yes, we were doing HB.
Is it always, I remember, originally when you wrote this in SI, like you ended up flipping which side you do first. So like it's the neighbors to the right times neighbors to the left, preferably, so that you could write it out, doublet of quartets. But does that also transfer over to saying that you want the smaller SP value to go first?
So it's not necessarily
like if your
SP. You have the right idea. It's just not the SP. It's just like the smaller number of neighbors.
Okay, you want that going first.
Yeah, just because you want the smaller times the larger. It doesn't really matter because if you have a quartet of doublets, you're still going to get the right answer. But just the most correct way is like that.
Got it.
Okay, so you have to pick which hydrogen to do it on?
Yeah, so he's always going to tell you, like, you wouldn't just be expected to look at this and be like, oh, the multiplicity is 8, right? Because that doesn't mean anything. He would tell me the multiplicity of HB. And at that point, you're like, all right, so I'm finding the splitting for this one. And I know this one has 2 neighbors. And I know they're different J values. And then we work from there. So he would have to tell you which one you're looking for.
Okay, thank you.
You're welcome. So I'm actually going to show you one more example because this is like a real complex splitting question, but he likes to be like, theoretically, if these weren't the same, what would you get? So if he says something like, theoretically, JAB does not equal JBC. So let's say we have something like this. And he's going to say find the multiplicity of HB. And he'll tell you this is HB, this is HA, and now this is HC. So at this point, these are all sp3, right? So this wouldn't be complex splitting. This is just normal splitting. But he's telling you specifically, pretend that that J value is different. So we're going to pretend it's a complex splitting question, right? And he tells you specifically, again, find HB. So you guys tell me, whoa, that was weird, what to do.
The one question I have for you is which one would be the neighbors to the left and which one would be the neighbor? Oh, wait, never mind. I answered the question for myself.
Okay. So
can I be the answer?
Yeah, go for it.
All right. So would it be 2 plus 1 on the left side, and on the right side it would be 6 plus 1. So it'll be 3 times 7. So the multiplicity is going to be 21.
Yep. So just to recap, we just did the same thing we did last time where we started with a smaller number and we did 2 plus 1, and then we did the big number, 6 plus 1, and we get 21. What would the name of this be?
A triplet of septets.
Yep. A triplet of septets. Hello to the people who just came in. I don't know when you came in, but I just realized there's more people. So hello. So does this make a little bit more sense than like when you came in?
Yes.
Okay, good. Ignore like what's going on this page, but I'll zoom out so you can take a picture if you want to. Plus, this is being recorded, so.
By the way, I'm sorry if you guys hear my dog snoring in the background. I know she's loud. I don't know if you can hear.
Dog content here. All right, so Luke had asked to do just some like practice problems. To the new people who came in, is there anything specific you want to work on, or is practice problems cool with everyone?
I'm okay with practice problems. If maybe we could also like touch on like the end of chapter 11 that we did yesterday in the review, which is like oxidation and stuff.
Yeah.
That sounds like a good idea.
Yes.
Okay, let's.
Cool. So yeah, we will do a couple of these chapter 9 problems, and then we'll skip to chapter 11 and we'll do some conceptual stuff. And then if we have time, we can do some practice problems for that too, which I don't think should be a problem because I'm here forever. So, all right, for chapter 9 for NMR, what is the first thing we look at when we're counting signals?
Symmetry.
I have a question.
Yes, what's up?
Can we, like, on his, like, practice problem set that he actually sent out, can we do a couple from, like, 30 through 38, where it's just, like, the charts and he's like, oh, figure out what it is?
Yes. We're going to do
Okay.
a couple of these, like, straightforward ones, and then we're going to look at the other, like, the spectrum ones, because those are usually scary, but they're not as bad as they look. So, yes, okay.
How long is this session?
Sorry, what was that?
How long is this session today?
So, it's until 12, and then I have another one from 3 to 5, but you can, like, come and go whenever you'd like.
Okay, got it.
So, yes, the first thing we look at is symmetry. So, we know that everything up here is going to be exactly equal to everything down here. So, we have one signal in this corner. 2. Are there any hydrogens here?
No.
No, because there are 4 bonds. Cool. And then one signal here and one signal here. So, altogether, how many proton signals do we see?
4.
4. Cool. Pretty straightforward. You just have to remember, like, symmetry, and you have to remember that hydrogen does not exist here because you only have 4 bonds. One that's a little tiny bit more complicated is this guy. So again, we're looking at proton NMR, so we're looking at hydrogens. Do we see any symmetry here?
We have partial symmetry.
We do. So this is going to be symmetrical down the middle, right? And that's a weird way to draw that, so whatever. But we can basically say that this and this are the same. This and this are the same. And then this is all by itself. And then on the opposite side of the oxygen, we have 1 and 2. So in total, someone said it in the chat, we do have 5 signals. Ignore my dog in the background. He's having a moment. Also, I have a bird, so if you hear just screaming in the background, I promise I'm not, like, torturing a child. I have a very loud bird. Okay, so before we move on, what is this functional group?
A functional.
It is definitely a functional group. It's an ether. And the way I want you to remember that is an ether is an oxygen with a carbon group on either side of it. Versus a lot of people mix it up with an ester. And an ester looks like this. Ta-da. Alrighty, so this next one, again, we're just talking about hydrogen NMR, and I'm going to draw this out for you. Stop it. Thank you. So we have 1, 2, 3 carbons. We have a chlorine here, and we have a bromine here. So do we have any symmetry? No. Cool. But what is something that is different here than the last couple that we did?
We have 2 atoms.
There's a potential chiral center.
Yes, so you guys were kind of getting at the same thing. We have this bromine and we have this chlorine. And the reason that's important is because this is a potential chiral center. The reason it's a potential chiral center is we have two separate groups and two hydrogens. And not more importantly, but we could see that this is a chiral center because we have 4 distinct groups. So since we have a chiral center and a potential chiral center, what's the relationship between these two hydrogens?
Diastereotopic.
Yep. Which means they are completely different. So, go ahead. Oh, I thought you were going to say something. Never mind. So this will be signal number 1. This will be signal number 2. Number 3. And then all of these 3 at the end are exactly the same. So this would be signal number 4. Bam. Any questions? Okay, I'll leave it up for a second and then we can move on. Okay, this is another way he could give you the complex splitting question, and it's just a lot of words. Wait, hold on. Okay, so question about the last one. Can there be diastereotopic and homotopic signals on the same chain? Yes. So again, diastereotopic, homotopic, heterotopic, and anisotopic, all of those are just comparison words. So these two compared to each other are diastereotopic. But this guy compared to this guy would just be heterotopic. They're just completely different from one another. This hydrogen compared to this hydrogen is homotopic because they are exactly the same as one another. So it just depends on which hydrogen you're looking at. Okay, cool. All right, so all you have to take away from this big long thing is you're looking at carbon number 2. We're looking at 1,1-dibromopentane. And we're saying that the coupling constants are sufficiently different. So let's draw out 1,1-dibromopentane. 1, 2, 3, 4, 5. Okay, cool. No, just kidding. I was looking at it and I was like, that's not right. Okay, so I'm drawing in these hydrogens for you. Ta-da. So carbon 1 is going to be the one with the 2 bromines. So this is carbon 2. Sorry about that. So carbon number 2, we're going to say that carbon number 2 versus carbon number 1 and carbon number 3, those are going to have different J values, right? We're just going to pretend. And these practice problems are from his set that's on campus. If you're in Dr. West's class. If you're in Dr. Roche's class, I emailed them to you a couple days ago. So J value doesn't have to do with shielding. J value just has to do with like neighboring protons and splitting, whereas shielding is kind of just more like chemical shift, things like that. Essentially all he's saying is that the coupling constant is different, so we're going to pretend that we have complex splitting here. Yeah, exactly. So we're going to use the n plus 1 times n plus 1. And since we're looking at these hydrogens, I'll go ahead and highlight the neighbors. So on the left, we have one neighbor, and on the right, we have two neighbors. So I'm just going to go ahead and fill in one yellow neighbor, so that's 2, times 2 red neighbors, which makes 3. Ta-da. So what would the name of this be? A doublet of triplets, exactly. So ta-da. Any questions about how I did this, or how to read the question, or anything like that?
Yeah, so I would be totally confused when it says consider splitting the C2 proton. I feel like that totally threw me off.
Yeah, it's one of those things that, like, this question, like, answering it is not that hard. It's just reading the question that's difficult. So again, all you really have to look for is, okay, C2, that's what we're doing. They're sufficiently different. Cool, we're pretending it's complex splitting, and then the actual name of the compound. There's a lot of questions like this where he just gives you a lot of junk. And so when you read it, just look, okay, this is what he's actually asking me.
So we knew that was C2 because we like counted like the way we would count a parent chain or like a main chain.
Exactly. So this would be 1, 2, 3, 4, 5. And then it could have been like any of them. He could have given you C3, 4, 5. It doesn't really matter. So it's not necessarily just like C2. It's the fact that he's asking what is the theoretical multiplicity of C2. So you know that's the one you're looking at, whatever it says there. C2 is just carbon number 2. So on the chain, if we start counting here, we have carbon number 1, carbon number 2, carbon number 3, 4, 5. Yeah. It's a weird way to write that, but that's all that means. Okay, so for this next one, the first thing we look at is splitting. The first thing we look at is symmetry. So we're going to cut this in half. And the next thing I would see is the double bond, right? So when do we have to care about a double bond? That's a weird way to phrase that, but so yeah, the double bond is going to matter when we're looking at diastereotopic protons, right? Because those are going to be two different signals. And in order to be diastereotopic as a double bond, you have to have two unique groups on one carbon, and you have to have two hydrogens on another carbon. So let's look at this double bond, right? We have this group and this group. Those are completely different from one another. So we have two unique groups, and we have two hydrogens. So those hydrogens are going to be completely different from one another. So we'll call this signal number 1. What am I doing? I don't know. Signal number 2. And that's going to be exactly the same on the other side. So this will be signal 1. This will be signal 2. So then from here, we know that this hydrogen is signal 3. And we also know that these methyls are exactly the same, so that will be signal number 4. So we can get rid of A, C, and D. Now between B and E, which one do you guys think is correct? Ooh, okay, someone said all singlets, and that's the trap that he wants you to fall into. But we know that since H1 and H2 are different, this is going to count as a neighbor. So they're going to split one another. So this is a doublet, doublet, and then these two are singlets. So the answer would be E. And I'll zoom out so you can see them. Any questions about these two? Okay, so how are they doublets? So since they're two completely different signals, let's start with the one that I just made purple on top. So we're going to count 1, 2, 3 bond lengths, no neighbors. 1, 2, 3 bond lengths, no neighbors. 1, 2 bond lengths, we reach a neighbor. So 1 neighbor plus 1 equals a doublet. Same exact thing for the one on the bottom. And the reason they're going to count as neighbors to one another is because they're diastereotopic. So they're two completely different signals, and they will split one another.
Wait, so they don't need to go through 3 bonds?
No, they have to just be within 3 bonds. So that means 3 or fewer. So if it's 2, that's completely fine. So yeah, the CH3s couldn't count as triplets or anything because those are all one signal. The only reason those two can split one another is because the double bond makes them diastereotopic. Exactly. Cool. And then I know you literally just asked your question, but I don't remember if I answered it or not.
Was it me?
Yeah.
Oh, you answered it, yeah.
Okay. Perfect. Alrighty, so let's do, okay, cool. Yeah. Let's do this one, and then we'll get to blah, blah, blah. We'll get on to the spectrums, or the spectra. Okay, so right quick, someone asked, can we do a problem with cozy and het core? I'm going to be completely honest with you guys. If he asks you questions about that, it's literally going to be like, what does cozy stand for? And we know that that's correlational spectroscopy. Or what does cozy tell us? And cozy just tells us about the relationship between adjacent hydrogens. And then with het core, it's literally just what does het core stand for? And that's heteronuclear correlation spectroscopy. So he's not going to ask you any kind of like real question about those two. It'll be like a naming question, super straightforward. You're very welcome. Okay, so he could give you like a bajillion questions similar to this one. The biggest thing you have to take away from it is it consists of a singlet, a doublet, and a triplet only. So we're going to go through these guys and figure out which one has only 3 signals, and they have to be a singlet, a doublet, and a triplet. So 3 signals doesn't sound like a lot. So I'm going to go ahead and start with the one that has the most symmetry. This one has symmetry right down the middle. So let's zoom into it. This has 1 signal here, 1 signal here. So that's too few. This one only has 2 signals. I'm going to get rid of it. This one is next door. This has partial symmetry. So I'm going to say this is signal number 1. This is signal number 2. Oh, cool. We have 3 signals. So we're going to keep this one for now. Let's go up here next. We have partial symmetry right here. So we're going to say that's signal number 1, 2, 3. Oop, we have 4 signals. We get rid of this one. Too many. Next door, partial symmetry. So this is 1 signal, 2, 3. Okay, cool. That one has 3. We'll keep it for now. Last but not least, partial symmetry. 1, 2, 3, 4. So we get rid of this one. So cool. Just by number of signals, we got rid of 3 of the answer choices. So we're stuck between 2 and 4. And now we have to figure out singlet, doublet, triplet, what's going on. So let's start with this one, just because. This signal has 1, 2, 3 bond lengths. Cool. It has 2 neighbors. Plus 1 equals a triplet. And then this one, we just said that it has this 1 neighbor. Cool. And there's no neighbors on the other side. So we're going to say 1 neighbor plus 1 equals a doublet. And then all the way over here, this hydrogen is not going to have any neighbors because there's nothing within 3 bond lengths. So it's a singlet. Does this match what he told us? Yes, so 4 would be the answer. If it did not match, you would just have to go and figure out what the multiplicity of each of these were, and that would probably be your answer. Any questions, comments, concerns?
This is more of a general question. So you have the 3 to 5 tutoring session and then none in person today, right? Just online?
Yep, so all of the sessions for today and Thursday are online, and then Wednesday and Friday are going to be in person. Okay, so let's look at number 2 because someone actually asked a question about it. So 1 bond length, 2 bond lengths, 3. So it doesn't actually reach the hydrogens, it just reaches the carbon. So this guy has 0 neighbors, it's a singlet. I'm sorry if you can hear everything going on in my house. This one has no neighbors on this side and 0 neighbors on this side. So this one is actually also a singlet. And then here, 1, 2, 3 bond lengths, nothing. 1, 2, 3 bond lengths, again, nothing. So all 3 of them are going to be singlets, actually. Okay, someone said I don't hear anything. Wonderful. Okay, so I think there was another question. And again, I already lost it. Okay, wait, someone asked what a coupling constant is. So a coupling constant and a J value are the same exact things. And let me just jump into here right quick. Okay. So this is literally just the coupling constant definition from your textbook, which I opened for the first time in like 3 years the other day. So the coupling constant is defined as the separation in frequency units of the peaks of a multiplet caused by spin-spin splitting. Okay, those are big words. What does that mean? Basically, think of the tree diagram very simply. So if we have one signal, we know that every one of those neighbors is going to break up that signal into multiple peaks. That's what we mean by a doublet, triplet, whatever, right? We have multiple peaks. So if we have these two peaks, we have some kind of distance here between them. So that distance between the two peaks is our J value. And that's in units of hertz. So how I want you to think about it is it's just the value by which one neighbor is going to split a signal. Cool? Yay? No? Yay. Okay, cool. So let's go back to this. And let's do this wonderful question that nobody likes, right? So first of all, we know that it's a hydrogen NMR spectrum because 1, it tells you, and 2, it only goes up to 8. So we know the smaller numbers are hydrogen spectra. Number 2, so he gives you the formula, and once in a blue moon, he'll give you an answer choice that doesn't match the formula. But honestly, I would not waste time with this. I would just go right to the spectrum. So with that being said, the first thing I like to do is the number of signals. So we can see we have 3 signals because there are 1, 2, 3 peaks here. So let's go through these answer choices and figure out which one has 3 signals. Remember symmetry. So we have 1 signal, 2 signals, no hydrogen here because there are 4 bonds, 3 signals. Cool, so this is a possible answer choice. The next one, we have partial symmetry here. So this is 1 signal, 2, 3, no hydrogen here because it's triple bond, no hydrogen here because it's a triple bond, 4, 5. Way too many signals. So we get rid of this answer choice. Next up, partial symmetry right here. So we have 1 signal, no hydrogen here, so we don't have a signal there. We have 1 hydrogen here. We have 1 hydrogen here. 4, 5. So again, way too many signals. We're going to get rid of this one. Next up, again, partial symmetry.
I have a question.
Yes, what's up?
For letter C, why is the hydrogens on the double bond isn't... Oh wait, there's only 1. I'm dumb.
Exactly. No worries. So yes, there's only 1 on each side. All right, so for this one, all 3 of those are exactly the same. No hydrogen here, no hydrogen here, no hydrogen here. 2, 3. Cool. Finally. Last but not least, these 3 are exactly the same. 1, no hydrogen here. 2, 3. We do have a hydrogen here. It'll look like that, but that's 4 signals, way too many. So, or not way too many, but still too many. So we get rid of that one. So just based on the number of signals, we can get rid of 3 answer choices. So you're already down to 50-50. Cool. The next step kind of like depends on what signal you have. I like to look at this and say, okay, chemical shift region, everything's in the alkyl region. The thing that sticks out to me most about this spectrum in particular is we have an integration of 9. Right? So let's look at our 2 remaining answer choices and see which one has a possible integration of 9. So this guy is the same as this guy. So we have 1, 2, 3, 4. 1, 2, 3, 4. 3, 6. So the highest integration we have here is 6. If we go down to D, all 3 of these methyls are symmetrical. So we have 3, 6, 9. 9H. And then we have 2H. And we have 3H. And let's see if this matches up. Wow, it does. So our correct answer is D. I know we went through this kind of fast. Does anyone have any questions, comments, concerns, anything of the sort? Yeah, okay, so this is something that he might not have made super clear. So these numbers are just the integration. So that's just the number of hydrogens per signal. I'll zoom back out. Oh, excuse me. Alrighty. What does it mean by electron impacts? I have no idea what you're talking about. Oh, someone actually did tell me, if you're not talking about this question, you're just talking about in general. Someone told me that there's like a question in the practice problems that says something about like electron impact or what signal. Yeah, I have to look at the summary sheet. I'm not sure what the context is. Did he email that to you guys? Did he post it on Canvas? On Canvas? Alright. Let me look at that right quick. I'm going to stop sharing my screen though. He words things in a really weird way, just to be difficult. Modules. Chapter summaries. Chapter 9. Yeah, I still don't know what you're talking about. Maybe I'm just like not looking at the same thing. So I'll show you what I see. So this, right? And then we're going to ignore IR because he didn't talk about IR. So where is the impact thing that you're talking about? Let me read it one more time. I'm probably just skipping over it. Oh, electron impact. Duh. honestly, off the top of my head, I don't know what electron impact is talking about. If you send me an email, I can look back at the PowerPoint and let you know. No worries. Okay, so done with that. Let's go back to here. Alrighty, so another one of these spectrum ones. This is one where I would say, okay, there are two different chemical shift regions. So alkyl, heteroatom. I just like to define that because it makes it easier. And first things first, we have 4 signals. So let's look at which one of these have 4 signals. First thing we look at is always symmetry, right? There's no symmetry down the middle, even though it almost looks like there is, but we do have symmetry internally. So we're going to have 1 signal. Why are you like this? 1 signal, 2 signals, 3, 4. Okay, this one matches. 1, 2, 3, 4. Okay, this one matches. Here we have, again, internal symmetry. So 1, 2, 3, 4. Annoyingly, this one still matches. Cut it in half. 1, 2, 3. Cool. This one doesn't match. Get rid of it. For this last one, these two are symmetrical. So we have 1, 2, 3, 4, 5. That's too many. Cool. So we can still get rid of 2 answer choices, and we're left with A, B, and C. And again, the big thing that sticks out to me here is we have a 6H signal, and it's in the heteroatom region. So I'm going to look for a 6H signal that's in the heteroatom region. Zoom back into this first one. Okay, so we do have a 6H signal, but we know that in order to be in the heteroatom region, it has to be either directly attached to a heteroatom or 1 carbon away. So this is incorrect. These are not in the heteroatom region. For this next one, only this is in the heteroatom region, and it's a integration of 2. So this has to be wrong. Next up, 6H, and it is in the heteroatom region. So C is correct. And we did that again kind of fast, so if you have any questions, let me know. If you want me to go through that last part again, I can definitely do that. You're very welcome. Have a nice day.
These aren't too bad.
Okay, cool. They look a lot worse before you actually get into them. All right, so do you guys want to do a couple mass spec questions, or do you want to go into the chapter 11 stuff? Okay, someone already said yes, so let's just do this right quick. Okay, so we are trying to figure out which one of these structures matches this mass spec. So we have 4 main things that we look for: the base peak, the M+ peak, the M+1, and M+2. Remember, we don't always have an N+2. The first thing that sticks out to me is this super tall one. So the absolute tallest peak in the whole spectrum is going to be the base peak. And this is going to be the most stable fragment.
Is this also the parent peak, the N plus peak in this case?
No, but good question. The reason it's not is because to find the N plus peak, we're going to go all the way in this end, right? And we know that the N plus 1 peak or the N plus 2 peak are going to be the absolute last peaks here, right? So we have this super tiny thing, and then this. If it would load, there we go. So we're going to say that the tallest peak on the end of the spectrum is the M plus. How I like to think of it, though, is the absolute last one has to be M plus 1 or M plus 2, right? And if it's super, super tiny like this one, we're going to say it's M plus 1. If it's taller, we're going to say it's M plus 2. Because M plus 1 is always super, super, super tiny. So I know automatically that's M plus 1. And that's M plus 2.
And that looks to be like a chlorine, right?
Yes, and why do we say it's a chlorine?
Because it's 30% of the parent peak.
Exactly. So the M plus 2 peak is approximately 1/3 of the M plus peak. So that means we probably have a chlorine present. Cool. So out of these answer choices, the only one that has a chlorine present is this. But let's just double check, right? 2 of the answer choices have nitrogens in them. So how do we know if there's a nitrogen present?
If the N plus peak is at an odd number. So
exactly.
yeah.
So if the M
Which
plus
is not.
peak, sorry, go ahead.
I said which is not. That's awesome.
Exactly. So yes, this is mass spec, and if this guy was at an odd number, we would know that there's an odd number of nitrogens, but it's not. It's at 78. So we can get rid of this right off the bat. But yeah, we already said that this has to be a chlorine. This is the only answer with a chlorine in it. So this is our correct answer. If we just want to double check, we can look at the mass of this. So we have 1, 2, 3 carbons times 12. And then we have 3, 6, 7 hydrogens times 1. And 1 chlorine times 35. So if you do some quick math, you get 78, which matches up with our M plus peak, so we are correct. Any questions about anything I did with this one?
Question, you said you figured out it was chlorine because it was 1/3 of the. How did you know that?
Okay, so let me just erase some of the stuff. So this peak right here is our M plus peak, right? And this is our M plus 2. So this peak is approximately 1/3 the size of this one. And let's make this red. And let's duplicate this. So 1, 2, 3. So if we had 3 of these peaks, that would equal 1 of this peak. If it was exactly the same height, that would be a bromine, and if it was super tiny, it would be a sulfur or an oxygen, but we don't care about those two. Also, welcome to the new people who came in. All right, cool. So I'm going to move on. If you have questions, we can definitely go back. Okay, so for this one, he's just asking for the formula. He's not asking for structure, which is awesome, and he only gives you 3 answer choices, which is even better. And he gives you a little hint on top. So all right, I don't know what the point of that is. This is basically just saying that this is super, super tiny compared to this one. Cool. We know that it's going to be tiny. That's always the case, right? So this is the absolute tallest peak. So we know that this is the base peak. And then if we go all the way at the end here, there's one super, super tiny peak at the end of it. So I'm going to go ahead and say that that is the M+1. And we don't have an M+2. And the one before it, right here, that is the M+ peak. So I'm going to zoom back out. Actually, I lied. So 90, 89, 88, 87. So I'll just mark it. Oh, just kidding. It tells you that right on top. Awesome. So if our M+ peak is at 87, what does that tell us?
We have a nitrogen.
We have a nitrogen, and we have an odd number specifically, so we can get rid of C because it has 2 nitrogens. And then between A and B, the way we figure out which one is correct is just by finding the mass. So for this one, we have 12 times 4 plus 1 times 9 plus nitrogen is 15 plus oxygen is 16. I don't know why I wrote that whole thing out, but that's fine. So this would be 88. And this one would be, I'm not going to write all of it out, but 12 times 5 plus 13 plus 15. Hold on. Not 18, 88. I think I did something wrong. Okay. 5, 12. Oh, I'm just being dumb. Hold on. Okay. They both add up to 88. The thing you have to look at here. I think I might have made this question. I think that's why it's messed up, to be honest. So this is supposed to be the correct answer. I think I just gave you an extra hydrogen. So that's my bad.
Does it?
Does it what?
Isn't oxygen? Well, couldn't we have known that from just seeing the oxygen, the NO, because that means that there's an M+2?
Yeah, exactly. That was the other thing that I was going to mention. So the oxygen would be an M+2 peak. It would be super tiny, but it would still be there. We don't have one here, so we know it's not A. And then I just messed up and I gave you one extra hydrogen, so that kind of messed you up a little bit as well. Does this one sort of kind of make sense? Yes?
Yeah.
Cool.
Yes.
Alrighty, awesome. So those are all the Chapter 9 practice problems I have for the review, I believe. Yeah. So you guys wanted to go back and do the stuff we did in SI yesterday. So I'm going to go ahead and switch back over and do that. I'll give you like one more second on this. And while I do that, I'm just going to disappear for 1 second and I'll be right back. Okay, so I pulled up the exam review thing from yesterday, the handout, and I emailed this to you guys. So oxidation is something we did last week, I want to say, in SI, and oxidation is basically just when we're making more bonds to oxygen. So super quick review of that. If we have a primary alcohol with a strong reagent, we're going to make a carboxylic acid because we have 2 hydrogens that we can replace. If we have a primary alcohol with a weak reagent, we can only go as far as the aldehyde. And no matter what kind of reagent we have, if we have a secondary alcohol, you have to make a ketone. Any questions on oxidation? It's pretty straightforward.
Just really quickly, what was the difference again between the primary, the secondary, and the tertiary oxygen?
So primary alcohol is going to be 1 carbon. So 1 carbon equals primary alcohol. If we have 2 carbons equals a secondary alcohol. And if we have 3 carbons, it's a tertiary alcohol.
And I'm going off the question that's in the chat because I just want to review this for myself. The difference between a weak and a strong oxidizing agent is if, like you said, O4 or more. So if you see the O4 or something higher, it's strong. And if you see less than that, it's a weak.
Exactly. So I didn't write down all the strong reagents because those are in the handout. But so like if you see H2SO4, if you have 4 or more oxygens present, that's going to be strong. PCC and DMSO are your weak reagents. So that's kind of how you differentiate strong and weak. For reducing agents, it's a little bit more straightforward because we only have 2 reagents. A is strong, B is weak. PCC, you don't really have to worry about what exactly it is because it'll tell you just PCC. Just know that it's a weak oxidizing agent. Excuse me, I'm very tired. Okay, so moving on to reduction. So reduction is like the exact opposite of oxidation, but it's a little bit, there's like a little bit more to it. It's a little bit less straightforward. And I like to group reduction into two pieces. So we have group one. Group one consists of aldehydes and ketones. And aldehydes and ketones, we're going to say that they are more reactive. And more reactive means that they can, with any reagent. Ta-da. Versus group two is carboxylic acids plus esters. These guys are less reactive, only react with LiAlH4, which is the strong reagent. And I'm actually going to just, never mind, I guess. Bring this up here. Okay, so group one, like I said, is going to be aldehydes and ketones. And at this point, we're just going to go through like the simplified reaction. Like we're not going to go through every single step. I just want you to know that we can use either reagent, and we're going to have H2O at the end. And the really, really important thing here is for reduction reactions, we have our reducing agents, which are LiAlH4 and NaBH4. But more importantly, we have our reducing species. And the reducing species is just more specifically the actual thing that's doing the reducing. So the thing that is doing the reducing is H-, and that's because this is what's actually attacking the carbonyl carbon and reducing it. So if we go back here, or I'll give you a second to write that down if you need to. Alrighty. So we're going to use either reagent. We know that H- is the actual reducing species. So we're going to attack here, bring those electrons up, right? In the first step, we get O-. We added a hydrogen. And at this point, you can't do anything else besides protonate. So we're going to use H2O to protonate this negative charge. So I am lazy and I don't want to redraw this, so I'm going to duplicate it. And the only thing we changed is we add a hydrogen here, which makes the charge neutral. So I'm going to zoom out. And we're going to summarize this and say that an aldehyde plus either reagent equals a primary alcohol. Any questions on that first one? Nope. Okay. Cool. If you do at any point, just let me know. So this second reaction is going to be exactly the same. First step. I don't know why it took such a long pause. So we're going to get O minus, and we add a hydrogen. At this point, there's nothing you can do besides protonate. So we have water present. The O is going to steal a hydrogen, and we get an alcohol yet again. So it's exactly the same steps. The only thing that's different here is we have a primary alcohol. Here we have a secondary alcohol. So we can say that a ketone plus either reagent is going to equal a secondary alcohol. So yeah, in general, aldehydes and ketones, when they're reduced, are both going to make alcohols. All of this stuff is going to basically boil down to a carbonyl equals an alcohol. It just depends on like what kind of alcohol you get, if that makes sense. Okay, cool. So that's group 1 in a nutshell. The difference for group 2 is going to be carboxylic acid and esters have leaving groups. So I'm just going to write that down. Biggest difference is that they have leaving groups. So I'm going to zoom in again. Let's do an ester because in SI I did a carboxylic acid. So we know that we have to use LiAlH4 because this is less reactive, and we know we have H2O. But we also know that the actual reducing species is still H-. Sorry about that. So we're going to attack here, kick up these electrons, just like we did in the first one. Someone said I had to look away for 2 minutes, and now we're miles away. I know, this moves so fast. I will zoom out so you can kind of take a look at what we did. And I'll try not to write super ugly. So in the first step, we kick those electrons up. We get a minus on our oxygen. And we still have our O here. All we've done is add a hydrogen. Right? Up in group 1, at this point, all we did is protonate. But here, the difference is we have a leaving group. So the leaving group means, I'm going to zoom back in, that we can reform this double bond instead of protonating, and we can kick off that leaving group. The reason this is considered a leaving group is because it is a heteroatom. So a carbon bonded to a heteroatom, we can break this bond. That's why it's a leaving group. Versus a hydrogen and a carbon, those are not going to be leaving groups. Alrighty. So at this point, we reform the double bond. We have a hydrogen, and this guy is floating off by itself. But functional group did we make? Not a ketone, because it has, yes, it has a hydrogen, so we're going to call it an aldehyde. A ketone is just different because it has another carbon here. All right, so at this point, we are not done, unfortunately, because an aldehyde still has a carbonyl. As long as we have a carbonyl, we're going to continue reducing. So we're going to say that there's more reducing agent left in solution. So this guy comes and attacks one more time. We get O- again. At this point, we can't do anything else besides protonate, as someone just said in the chat, because there's no more leaving groups or anything. So we are just going to use our H2O and protonate the O- into an alcohol. So bam, bam. And now our alcohol is going to be primary because we have 2 hydrogens attached to it. So in summary, we can say that an ester plus LiAlH4 equals a primary OH. And in parentheses, I'm going to say we reduce twice. And I'm not going to redraw the whole thing again for carboxylic acid because we get the exact same answer. So I'm actually just going to copy and paste it so you guys can like take a picture if you would like to. Literally the only thing that changes is this. And we get the same exact answer. So we're going to say a carboxylic acid plus LiAlH4 equals a primary alcohol. Let me zoom out a tad so you can see this whole thing at once. And there are a couple practice problems for this, so we can go over that in a sec. Any questions, comments, concerns, anything like that for reduction? Alrighty. If not, the last thing we covered... Okay, someone says straightforward. That's awesome. I think it's kind of straightforward too. Alright, so we're going to take this information and we're going to branch off into a specific kind of reduction. And we're going to call that a Grignard reaction. And someone asked about the average for the first exam. So for Dr. West, the averages are all pretty much like a 70-ish, 72. The first exam is a little bit lower usually just because of the timing. People aren't used to it and people tend to get like surprised by it. But it's still usually like in the 70s. Which is like an average, like, it's an average. Most classes have like a 75-ish average. Yeah, it's not too crazy bad. In Orgo 1, it was like in the 60s. So, yeah. Orgo 1 was a bad time. Alright, so the Grignard reaction is actually going to be not multi-step, but we're going to look at how to make the Grignard first. So, all right, I will explain this in the soap opera kind of way that I did in SI and in the review session. So if you're hearing it for the third time, I apologize. We are going to start with an alkyl halide, and just for funsies, I'm going to change the alkyl halide. So, in this alkyl halide, this carbon and this bromine are in a lovely relationship. They're so happy, they're bonded, they've been together forever, super happy, right? But then, one day, magnesium comes along, and magnesium is going to be a huge hoe. Like, magnesium is a homewrecker. We hate magnesium, right? Magnesium's going to come in and just insert himself right here in the middle and break them up, right? So we get carbon right here, and carbon thinks he's still bonded to bromine, but in reality, magnesium came in and is right in between them, right? So even though it looks like this to the outside, we know what magnesium did. We know that magnesium came and broke them up. So the Grignard reagent is what we get when our carbon realizes that he is all alone and his love has been taken away by the hoe magnesium. He's really negative. He's really sad. So sad face, magnesium took it away. It's negative. It's really sad by itself. It wants to make a new bond, right? It doesn't want to be single and all alone. So this guy is actually going to be a very strong nucleophile, and it can also be a very strong base. So we're going to take a quick detour from our actual reaction, and we're going to say what is a strong nucleophile versus a strong base. So a nucleophile is going to use its electrons to attack and attach to a molecule. Versus, bam, the base is going to use its electrons to steal a hydrogen. And someone said, so the magnesium and bromine basically fall off like a leaving group. Yeah, we can think of it that way. Short answer, yes. Long answer, this is actually a really weird bond. So they're connected, but they're not really connected. So we could just basically, like, we draw it as a bond, but we actually look at it as if this was like a spectator ion, almost. So they're not really connected. So they basically fall off like a leaving group, kind of. Yeah, it's basically just like floating around in solution around it, kind of thing. All right. So now that we know, sorry, yawning again. This is the Grignard reagent. We know that it could be a strong nucleophile or a strong base, so we're going to see it in action. So again, this was just creating the Grignard. This isn't the actual Grignard reaction. The Grignard reaction is going to look like this. So any kind of, actually I don't like that. I'm going to start with an aldehyde. So any kind of carbonyl is going to react with a Grignard reagent. So let's use the same one we just made for funsies. So our Grignard reagent is really, really sad and all alone. So it can do one of two things. It can either be a nucleophile and attack this carbon, or it can be a base and it can steal a hydrogen. So we're going to go back here for 1 second, and we're going to define what an acidic hydrogen is. It can't do both at the same time. No. All right, so in order for it to act like a base, we need to have an acidic hydrogen in solution. And specifically for Grignards, we have a very specific definition for an acidic hydrogen. So this is going to include carboxylic acids, heteroatoms, and triple bonds. So basically, if we have a hydrogen on a carboxylic acid, a hydrogen on a heteroatom, or a hydrogen on a triple bond, this will choose to steal that hydrogen instead of acting like a nucleophile. That's basically all that means. So let's go back here. All right, so someone asked, so it's going to act like a base here? No, because we don't have an acidic hydrogen, right? Because like we said, acidic hydrogen is going to be very, very specific. This hydrogen is attached to the carbonyl. So in that case, we're going to say it's not an acidic hydrogen. I'll show you what an acidic hydrogen looks like in a second, but let's do this reaction first. So we're going to act like a nucleophile. We're going to, bam, attack here and move those electrons up. Yes, we're going to attack the carbon. And just like in the reduction reactions we just did, we get O minus. The only difference is now, instead of adding a hydrogen, we're adding this carbon chain. So I always, always, always say count your carbons. 1, 2, 3, 4. So we're going to make a bond to carbon 1. Carbon 1 is then attached to carbon 2. And then we have carbon 3 and carbon 4. At this point, just like our reduction reaction, we don't have anything else to do. We don't have any leaving groups or anything, so we have to protonate. So someone said form the double bond. That's a wonderful idea. We could do that if we had a leaving group. But in this case, we have a hydrogen. We can't get rid of a hydrogen, so we're just going to protonate. So we're going to, bam, steal the hydrogen, bam. So we get H. The reagent that we just added. And now we formed an alcohol. Ta-da! So this is the Grignard reaction. You're very welcome. Bye-bye.
Thanks, Rose. Bye-bye.
Alrighty. So the Grignard reaction, what was I thinking? Yes, okay. So someone said reform the double bond. So let's see what this looks like if we have a leaving group. Bam. And just to remind you that the Grignard reagent can really look like anything, I'm going to give you this now. Actually, I lied. Okay, so if he gave you this, we know that this piece of it isn't really there, and we're going to replace that with a negative. So we actually have this as our Grignard reagent. And we know it's going to act like a nucleophile because we don't have any acidic protons present. So we attack and kick up those electrons. So we get O- again, just like last time. I will answer your question in 1 second. Again, we're going to count our carbon. So I'm going to call this carbon 1, 2, and 3. And when we attach it to our group, we're going to attach to carbon 1. And then that's going to have carbons 2 and 3 on it. Not dumb. Not dumb at all. So the question was H2O doesn't really do anything. H2O is just going to come in at the very last step, and it's going to protonate the O-. Okay, so... excuse me. Oh my gosh, so tired. All right, so now we have a leaving group present. So instead of protonating, we're going to drop this double bond back down, kick off the leaving group, and we get this. Now, since we have a leaving group and we reformed our double bond, we are going to react again. So we're going to assume we have enough of our Grignard reagent to attack again. And we go bam, bam. Gives us an O-. And we are going to have 2 of the Grignard reagents present. Now at this point, we really have nothing to do. So we have to protonate. Bam, bam. And we get an alcohol again. And now we've added 2 of the Grignard reagents. So we can say if we have no leaving groups, we're going to add 1 Grignard. If we have 1 leaving group, we add 2 Grignards. What if I gave you this? What do you think? Exactly. So we got 2 answers. One says that it's a leaving group, so we would attack twice. And the other one says, isn't this an acidic hydrogen? Yes, it is. So the negative charge will act like a base in this case, and it will just steal this hydrogen. And we can consider that no reaction. So what I mean by no reaction is no Grignard reaction happens, just acid base. This would be the same thing if we had something like this, right? So now it's just a ketone, but there's a heteroatom, and so this counts as a acidic proton. Same thing here. Let's say we have this, and then we have a triple bond with a hydrogen on it. This is an acidic proton, so we would get no reaction. Let me zoom out just a tad so you can see this. Any questions, comments, concerns, anything of the sort?
Can you like re-explain what an acidic hydrogen is?
Yes, absolutely. So for the purposes of this reaction only, we have a super specific definition of acidic hydrogen. So we're going to say that the hydrogen on a carboxylic acid, on a heteroatom, and on a triple bond are acidic. So I'm going to take this and I'm going to rewrite it, and I'm going to give you an example of each one. So acidic H. For the Grignard reaction specifically, we're going to count carboxylic acids. So specifically, if we have a carboxylic acid, this hydrogen right here is considered acidic. If we have a heteroatom, so if we have an OH present, the squiggly line just means that that's attached somewhere on the molecule. So if we have a carbonyl with an OH somewhere, this counts as acidic. In addition, you won't really see this, but let's say we had something like NH2. Nitrogen is also a heteroatom, so this would be considered acidic. And the third example is a triple bond. So if we have a triple bond attached somewhere, and we have a hydrogen attached to it, this hydrogen counts as an acidic proton. So for the last two, I will show you like an example of what that might look like. So let's say we have a ketone, and a couple carbons away, we have an OH. This hydrogen will be acidic, and the reaction won't happen. Same with a triple bond. Let's say we have like an aldehyde, right? And then on the end, we have a triple bond. This hydrogen is too acidic, the reaction won't occur. Is this a little bit more clear written out like this? I'll specify for cool. Okay. Alrighty, guys. So it is almost 11:50. We have a couple minutes left, so I don't want to like start anything new. But do you guys have any questions, comments, concerns about anything we did today? Anything you want me to go back and show you? Any clarifications? Anything at all? So the recording here, let me send you. Let me sell you the link. No. Let me send you the link to the YouTube channel where it will be uploaded. You are very, very welcome. Someone said, I wish I had more time to study. I feel you. It feels like there's never any time. Yes, there's another meeting at 3, so it'll be from 3 to 5 p.m. And the recordings might take a little while to upload. I am also trying to upload yesterday's session and the exam review session, but they will be up by the end of today. Okay. Aw, thank you. You guys are so cute. That's all right. However you want to join, if you can't participate, that's fine. All right. So if there's no more questions, I will let you guys go for now. And whoever will be here at 3, I will see you later. And if not, I will see you tomorrow or at the exam or whatever.